Hi there, this is Lab 3 project, part 2. It's the 2D flow over cylinder, and this is for a viscous or inviscid case at 30 hertz or 60 hertz. Inviscid case at 60 hertz. So here is the model. So this is the wind tunnel that from Lab 1, and then just a small circle of radius d inside of it. And then that was inserted into Fluent. And don't mind this one. This one is just a test case. But so we inserted the geometry here, and then we meshed it. So let me open up the meshing. I'm just recording here. Just gonna. So here's the mesh. It's a little hard to see on here. However, here's the mesh. So just did an edge sizing to for the circle and a face sizing for the face, and then we named all the edges, so inlet, outlet, wall, and then sphere for the wall on the inside. And then inserted this into Fluent. So I'll open that up real quick. Yeah, you took precision into start that. So here is the mesh inside of Fluent, and I'll go through some of the settings that are important. Nothing really changed here. The biggest thing was models, energy turned on, and made sure that our model was inviscid here. So show that's inviscid. And then material, fluid, air. Made sure to have the density of the fluid as just a solid 1. And then boundary conditions. So make sure that everything is selected. Inlet is a velocity inlet with a velocity magnitude of should be 5.1, I believe. And that is calculated from Bernoulli's equation, because we know at 60 hertz, we can find the test section velocity, and then we can work back up because we know the geometry of the wind tunnel. So the velocity magnitude will be 5.1, apply that, close that, and then we will have the outlet as a pressure outlet, sphere as a wall, and then the walls as walls. And then we can go to method, and these are settings I found online from a similar project. So went to a simple scheme, and we did pressure, make sure we did presto for this spatial discretization. Everything else should be fine. Second order, least square cell based should be fine. And then initialized, we initialized with 35 iterations. So that, and then we ran a calculation, the 150 iterations. Actually, we can do, is it motors? I'm trying to figure out where you see all the um, here. And trying to figure out where you see the stuff. Initialization. Motors. Anyway, and then we will run the calculation, the 150 iterations, calculate that. So here is our solution. And then we can check this by going to plots, XY plot, and we can determine the pressure coefficient versus the direction vector for the sphere. So let's load that plot up. And we can see, as expected, the pressure coefficient is going to be around, the highest it can be is around 1, and the least it can be is around -3. Obviously, this depends based on the conditions and stuff, but in a perfect inviscid flow, that is how it is. So this is within that acceptable range. And it's about the right shape as we should see in other simulations that I run. And then we want to run a velocity magnitude versus direction on the sphere. Save that. And again, we'll have this similar plot where velocity is going to be lowest near the front and the back, and then at its maximum near the top of the sphere. And this should look opposite of the pressure coefficients due to pressure and velocity being inversely related. So